France with presentation accuracy of machine learning technologies with forecasting tunneling-induced soil settlements with limited data.
Hello everyone, I'm Tatiana Richa, a geotechnical data engineer at XVIII in Paris, and I'm glad to be here with you today to present our work on the accuracy of machine learning techniques in forecasting tunneling-induced soil settlements with limited data. Nowadays, the need for underground tunnels is increasing, and sometimes in very diverse soil stratigraphies. We're seeing more and more automated excavations using tunnel boring machines, which help faster the excavation process. However, an important risk still remains, which are surface settlements that can damage nearby structures. To tackle this problem, we wanted to use artificial intelligence techniques to predict these settlements in real time. Our work is based on two lines of the Grand Paris Express, which are line 14 South and line 15 Southwest. Together they form about 13 kilometers of tunnel boring machine excavated lines in very diverse soil stratigraphies. To measure settlements, about 16,000 monitors were installed along these lines. So to be able to use machine learning to predict these settlements, we needed to first constitute a database with these categories: settlements, soil parameters, and tunnel boring machine operating parameters. Once we have our database, we can actually adopt this methodology to develop our machine learning model. So first, obviously, we choose the algorithms we want to work with. In our case, we wanted to test XGBoost, random forest, artificial neural networks, decision trees, and SVM. Second, we choose the metrics that we're going to use to measure the accuracy of the predictions. We chose RMSE and R-square. Third step is to divide the data set. Normally, we're going to take 80% of the database for the training set and 20% for testing. You should know that at this stage of training, we divided our data set randomly along both tunnel lines without really looking into the position of the tunnel face. And then we're going to train the algorithms and check if we have overfitting and what is the data set size that's sufficient to have enough accuracy. To do so, we're going to use cross-validation and learning curves. So what are exactly learning curves? We're going to actually variate our data set size, do the cross-validation, and then we're going to analyze using our metrics. In this case, we used R-square. And we're seeing here an example of a learning curve using random forest algorithm. And we noticed that about 700 observations were large enough to have enough accuracy. We see that the R-square is close to 0.9, 1 being the perfect score. So we went a step back and we divided our data set into only 30% for training instead of 80%. And 70% was left for testing, allowing us better performance testing. The next step is to regularize and optimize the model to obtain optimal results. So we're going to use the bias and variance trade-off to find the ranges of each of the hyperparameter for each algorithm. And then we can use random search or grid search to find the best combination of all hyperparameters together. And last step, obviously, we're going to analyze our results using different kinds of visualizations. In our case, we found out that XGBoost and random forest have the best results. So I just showed you a methodology to develop our machine learning model, but it does not really answer our need to have a real-time model to predict settlements. In my PhD manuscript, which is already online, I went into details to how to tackle this problem. But to say in few words, we can actually take all the data behind the tunnel face for the training and then train the model and use the obtained model for the prediction of the settlement in front of the tunnel face in areas that are not yet excavated. Our studies show that we can use the obtained model up to 150 meters in front of the tunnel face to predict settlements, which is equivalent to more than 5 working days. So that was actually very satisfactory in our case. And we showed as well that we can improve the model's accuracy with weekly or monthly training by taking into account new data arriving while excavating. So yeah, machine learning is very nice, but it definitely comes with its own challenges. And I didn't want to skip the chance to share with you the challenges that we actually had to deal with in our work. So as you know, field data is raw data that needs lots of treatment to become exploitable by machine learning algorithms. We're dealing with geotechnical data that's very sparse. We need to deal with duplicates, outliers, you name it. There's lots of problems with the data. But honestly, the major problem that we faced was really with the practical problem about the diversity of the suppliers. So this raises the question of the property of the data and the confidentiality level. And the next problem was the diversity of data formats. We have PDF files, CSV, all over the place. So we really recommend to impose universal data access modes like databases or interfaces in a structured format. So at Terrasol, we wanted to make that happen. So by developing our own geotechnical collaborative web platform named Orbu, and it deals with all, it answers the needs of all players in the geotechnical field. So we have finally one place for all our project data, where the data is digitalized in one place, so centralized. It is in a structured and protected database where we can share the data or not with our fellow colleagues. So this kind of structured platform can actually save us up to 80% of the unbearable task of data preparation for machine learning. So do not hesitate to pass by our stand at Terrasol, and thank you for listening.